This is part 3 of the inverse functions videos. We're going to review the concept of inverse functions, check that functions are inverses with a few specific cases, and then verify that they're inverses by checking all possible cases. So if we have a function and we think of it in terms of a function machine, maybe we want to call that function f, and we're going to put an input into the machine, and it's going to do a couple things. So maybe this function adds 5 and then multiplies by 4. So we're going to get out x plus 5 and then all multiplied by 4. And we could think about inputting specific values. So when I put in 2, I get out 2 plus 5 is 7. 7 times 4 is 28. So when I put in 2, I get out 28. And we could organize this information into a table, or we could write it as a function machine, or we could represent it on a graph. But this function machine is showing all of those possibilities because we haven't been specific about what x is. And if I wanted to find the inverse of this function, then I would need another function machine, and let's call that one g. And I want to do the same operations but in the reverse order, and I want to do the inverse of those operations. So instead of multiplying by 4 last, I'm going to divide by 4 first, and instead of adding 5 first, I'm going to subtract 5 last. So when I put in x, I'm going to get out x divided by 4 and then subtract 5. So if I want to check that these equations really are inverses, then I need to double check that they undo each other. So we just looked at if I input 2, I get out 28 for my f function. And so when I input 28 to my g function, hopefully I get out 2. 28 divided by 4 is 7, and 7 minus 5 is 2. So we see that these functions appear to be inverses in at least this one case. And we can check another case. When I put in, let's do negative 5. Negative 5 plus 5 is 0, and 4 times 0 is 0. And so when I input 0 to my g function, hopefully I get out negative 5. 0 divided by 4 is 0, and 0 minus 5 is negative 5. So these functions, f and g, do appear to be inverses, but we've only checked 2 cases. What if the next case we checked, it didn't work? Or what if we checked 1,000,000 cases, but the one after that didn't work? So we need a method that allows us to make sure these are inverses for all cases. So what I'm going to do is input x to the f function, and I get out my usual 4 times x plus 5. And then I'm going to take that and put it right into the g function. So I'm taking all of the outputs from my f function, because I haven't been specific about what x is, and I'm putting them all into the g function all at once. So I'm taking 4 times x plus 5, and I'm first dividing it by 4, and then subtracting 5. So when I take 4 groups of something and divide it by 4, I just get one group of x plus 5. And when I do x plus 5 minus 5, I just get x. So my output here is x. Now let's make sure that this is the result we wanted. We started by inputting x. We got an output. We took our supposedly inverse function, and we put our first output into it, and we got back to our original input from the f function. So we are seeing that these inputs and outputs are switched. And because we haven't been specific with what x is, we've just proven that it's true for all values of x. So looking at an example here, I've got f of x equals the square root of x plus 5 So that's saying to first add 5 to x and then take the square root. And I've got g of x, which says to square x first and then subtract 5. So I want to verify that these are inverses, which means I need to do it for every single value of x. And to do that, I need to input x to my original function, to my f function. Sorry, I have no original here. And I'm going to get out the square root of x plus 5. And then I want to take that and I want to put it right into my g function. And so what I'm going to get is the square root of x plus 5 as my input. And then I'm going to square it as my first operation and then subtract 5. So if I'm simplifying this, the square root of something squared is just that expression, x plus 5, and x plus 5 minus 5 is x. So I get out x here, which is what I was hoping for. This shows that no matter what value x takes, if you input it to one function, you'll get an output, and if you put that output into the next function, you'll get back your original input. Now if I wanted to do this without the function machines, what I would want to show is that when you take g of x and you input f of x, that you get back your input. So this notation looks pretty complicated, but what it's saying is take the f function and input x, and then take the g function and input f of x. And you should get back out your original input, which is x. So if I were showing this algebraically, I would take the g function, which is to take the input, square it, and subtract 5, and I would input the f function, which is the square root of x plus 5. And so this is g of f of x. And at this point, it should look familiar because we just saw the same algebra on the last slide. So the square root of the square of something that's been square rooted is just that expression, x plus 5. And when I subtract 5 from that, I get x. So we do see that g of f of x equals x. And we could do this in the other order. We could do f of g of x. And we should still see that f of g of x equals x if we did that composition of functions. Here's another example. We want to verify that f of x and g of x are inverses. F of x equals x divided by 3 squared plus 5, and g of x equals 3 times the square root of x minus 5. So this time I'll do f of g of x. So I'm going to take x, input it to g, I'll get out 3 times the square root of x minus 5, and then I'm going to take the f function and input what I just got. So I'm going to take the input, which is 3 times the square root of x minus 5, divide that by 3, square all of it, and add 5. So I've substituted g of x for x in my f function. So I've got 3 groups of the square root of x minus 5 divided by 3, which is just the square root of x minus 5. I'm squaring that and adding 5. The square of something that's been square rooted is just this. X minus 5 plus 5 equals x. It's totally a coincidence that I keep ending up with the same last line. I guess I just really like the number 5. But I do see here that when I input the g function to the f function, I get out x, because my original input to the g function was x. Alright, so I've got one more example. I want to verify that f of x and g of x are inverses. F of x equals 3x plus 45, g of x equals x divided by 3 minus 14. So if I do f of g of x, then I've got an x being inputted into the g function, which is going to get out x over 3 minus 14, and I'm using that as my input for the f function, so 3 times x over 3 minus 14 plus 45. So if I distribute that 3 in, I'll get x minus 42 and still have the plus 45. Negative 42 and positive 45 simplify to be positive 3. So when I do f of g of x, I get x plus 3, which shows me that these are not inverses. Alright, so make sure that you do the practice problem sets for the inverse functions videos, and email me and set up a retake for whenever you're ready.